Hi everyone, welcome back to Math 256 for the final episode of this course. So this is the last section we're going to talk about, and it's not very long. It's just a short little one. It's just like a victory lap on Laplace transforms. In particular, it's going to be about convolutions. Alright, so here's the basic idea. So there are other ways to get the Laplace transform for something other than doing partial fractions and breaking it down, or any of the other things we've seen. In particular, rather than using partial fractions, there are other approaches we can use. To get inverse Laplace transforms. And the main one that we'll be doing here is convolution of functions. Convolutions. So first off, the definition. The convolution of f and g is given by so the notation is f, then an asterisk g, so it's not times, it's a convolution, and that evaluated at t is equal to the integral that goes from 0 to t, and now inside the integral it needs a different variable. In particular, it will be f of tau, and then times g of t minus tau. And that would be with respect to tau. Now, what does that have to do with Laplace transforms? Well, it has something to do with integrals, so it shouldn't be too surprising that it has something to do with Laplace transforms. But here is the connection. So it's called the convolution theorem. So the convolution theorem says that if I take the Laplace transform of the convolution of two functions, then that is actually just going to be equal to the product of their Laplace transforms. And conversely, the inverse Laplace transform of two known functions, f and g, is equal to the convolution of their respective inverse transforms. So i.e., in particular, if we know the inverse Laplace transform of two factors that comprise a function, or I should say that make up a function. Grammatically, comprise is the other way. It should be the function comprises the two factors, not the two factors comprise the function. Common error. So the two factors that make up a function, we can take the convolution. To produce the inverse Laplace transform of the product. All right, let's just try this. For example, this is a replacement usually for partial fractions. Let's see an example where partial fractions would be what we would ordinarily instinctively do. So let's see. So find inverse Laplace transform of 1 over s squared plus 1. Okay, so we would always do this by partial fractions typically, but let's just have some fun. So here, let's just break it into the two pieces. So this is 1 over s squared times 1 over s squared plus 1. Now, each of these is very, very understandable. We can just say little a of t is equal to t. This is the Laplace transform of just t. And this, on the other hand, is the Laplace transform of, let's see, that's a k, so that would mean this is sine. So b of t equals sine t. All right, well then the inverse Laplace transform of a of s times b of s is going to equal the convolution of little a and little b, which in turn is going to then be the integral from 0 to t. This is going to be just tau, which is just the function that is the identity here. And then b of t is going to equal t minus tau, but inside the sign. All right, well, how are we going to integrate this? Let's use some integration by parts. So u will be equal to just tau, which means du would be just d tau. Okay, so far so good. dv will be sine t minus tau. And then v will equal, so tau is the variable with respect to which, d tau. Tau is the variable with respect to which we are integrating here. So a negative would come out, and then the antiderivative of sine is negative cosine. So altogether, it's going to make a positive cosine, t minus tau. And so what does that leave us with? It leaves us with tau cosine t minus tau. And this will be evaluated at 0 to t, and then minus the integral of v du. So it's going to be the integral of cosine t minus tau d tau 0 to t. So what do we have here? Put in a t, it's going to be t times cosine of 0, which is just, in fact, 1. Put in a 0, and it's going to be 0 times something, which is just going to be 0. And then here, we're talking about the integral of cosine, which is going to be then sine, but there's a negative inside on the tau, so that would come out. But there's a negative there, so that'll cancel, and that'll become, therefore, sine t minus tau. And it's going to be at 0 to t. And so what's that going to be? It's going to be t. Here, when you put in 0, it's going to equal just sine of 0, which equals 0, plus 0, minus, you put in a 0 for tau, and it's just going to be the sine of t. So what do we get? We get t minus sine of t. So that would be an alternative approach to finding the Laplace transform for this particular expression. Now, once again, this is a case where partial fractions would have been easy, but there are times when it is more convenient to write it as a convolution. One thing that I might note, in the last section we saw a function that broke up into its transient solution and its steady periodic solution. Well, it turns out that each of those pieces came from one of the factors in the denominator, if you'll recall. And so it is a common way of expressing the solutions to systems such as that as a convolution between the piece that represents the natural frequency and the piece that represents the forcing function. But that's again something that is not exactly a prime concern of ours in this course. It's more like an interesting application and side note. And just if you want, here are a couple other formulas that are sometimes found to be pretty useful in finding Laplace transforms. We won't really illustrate them right now, but just so you know that they exist and that you have them in the record, here are some other useful formulas. All right, some other useful formulas. So if Laplace transform of f of t is written as capital F of s, which is our standard notation, then here are some facts. The Laplace transform of negative t times f of t is equal to f prime of s. The Laplace transform of just positive t, f of t, is then therefore equal to negative f prime of s. So where this comes in handy is if you already know the Laplace transform of a certain function, and you are instead asked for the Laplace transform of t times that function, you can basically just differentiate what you know with a negative in front and get the new Laplace transform. All right. Sometimes though it's easier said than done differentiating the expressions, but at least differentiation is easier than integration. All right. So then by the same token, we can turn these equations around a little bit and say then that t times f of t is going to equal the inverse Laplace transform of negative f prime of s. So in other words, if now we turn the ball around, or we turn the coin to the other side, and we have a function that we're trying to find the inverse Laplace transform of, maybe it will be easier if we actually just integrate it rather than different, and then that would be adding a t to the inverse Laplace transform. And then finally, then one last twist on this is negative. So f of t is equal to negative 1 over t times the inverse Laplace transform of the derivative. This is just the most streamlined version of the same formula. So basically, if the function that you're trying to take the inverse Laplace transform of is a known derivative, then this would be a formula for its inverse Laplace transform. Then there's one more thing, it's called the integral formula. And this is kind of the same thing, but in reverse. So it's the Laplace transform of f of t, not times t, but divided by t. And this is equal to not the derivative, but the antiderivative. And because of that negative, the way that that's frequently expressed is to invert the order of the bounds of integration. And so it makes it go from s to infinity here, and it's going to be f of sigma d sigma. Again, I just wanted these to be in the record in case you ever find yourself on a desert island needing to prove them, or needing something to occupy your time. You can try proving these, you can try figuring out how to use these. And also, if you are in an engineering class, you're going to probably see some more Laplace transforms, and these might be good things to just have in the notebook. So the convolution theorem, that's something that we will actually use. The rest of these, it's just some interesting extra formulas that can be used sometimes to make one's life easier if the functions that we're talking about happen to fall into certain known patterns. All right, well, that's going to do it now. So that will be Math 256 for us. So it's been a wild ride. We've learned a lot. We've seen a lot. We've gone through a lot of problems. And I look forward to seeing you all on the other side. So till then, bye.